notes, page 9. How do we calculate these up launch problems? How do we calculate the throw up problems? Actually, pretty straightforward. You really have to pay attention to your givens. You've been doing a nice job paying attention to your givens. I'm going to ask you to step up your level again for these problems. Okay. Tip 1. Acceleration is due to Earth's gravity, and that is not going to change. So basically, when you have a throw-up problem, whether the ball is on the way up, on the way down, or even at the peak, in all cases, it will accelerate at 9.81 meters per second squared toward the Earth. It's really toward the Earth's center, aka down. Next, tip 2. At the peak, the object stops for a moment. I can't tell you how long that moment is because it's really a moment. Anyway, but it is still accelerating at g, at 9.81. So once we get to the peak, you get that instant of where everything is clear. So what that means is the velocity at the peak is 0. But don't be fooled, the acceleration is still 9.81. The velocity at the peak is 0. Remember, acceleration is based on changes in velocity, so you need an interval either before leading up to the peak or from the peak after. The velocity at the peak is 0. This can be a VI or a VF. Usually we will use this as a VF at the peak, although sometimes we can use it as a VI at the peak. All right, tip 3, we saw this from our video. It was fast down here, a little slower, a little slower, a little slower, a little slower, down to 0, and then again, a little fast, a little fast. They matched. And so at matching heights, your velocities will match. This is a very useful given as well. VI at the launch is going to be negative VF at the landing. The negative matters. If you don't put that in your equations, you end up getting something like 0 equals 0. Great. That doesn't make us any smarter. So VI at the launch is going to be negative VF at the landing, meaning the speeds match, but they're in opposite directions. Often you'll call this VI equals maybe 29.43 from the last page. And then you'll say VF equals, VF at the end will equal negative 29.43 meters per second. As you would probably guess, since everything is matching, this whole symmetry of free fall, we call it, on the way up matches on the way down. Actually, the time to go up matches the time to come down. The time to go up equals the time to come down. And since the time to go up, let's say 5 seconds. The last problem was 3 seconds. Let's say 3 seconds to go up, 3 seconds to go down. The total time is just going to be double that, 6 seconds. Of course, the time to go up is going to be half of the total. If the total is 6, the time to go up is 3, the time to go down is 3. Of course, that total is 6 divided by 2 to get each way. Okay, the last tip as far as givens go is as the object returns to its launch point, there is no displacement. D at the end equals 0 meters. This is a very useful given that often gets overlooked. You can use this to help you solve problems. Anywhere you can plug a 0 into your equations usually makes your life easier. Now, though there is nothing to write for tip 6, it is the most important of all. You must look at all this: up, down, end, VI, VF, launch, landing. You must know where in the problem that you have to solve and that you have been told. You must know the location within or along the trajectory. All of these, the peak, the end, the launch, they're going to come into play with your questions. So you're good at algebra. You're good at setting up the problems. Now you have to step up that game with the givens, as we mentioned before. If it's at the peak, certain things will be true. Something about the time. the velocity will be 0. The acceleration is still that 9.81 down. If it's at the end, the landing, you know the displacement will, for most cases, be 0. The velocity will be negative the initial velocity. The time now is the full time. Maybe you knew the half time, you can double it. Or we set you up by giving you a lot of these, or sometimes you get some other time or location. Not at the peak, not at the end, but 2 seconds in. Not at the peak, not at the end, but 10 meters above the ground. And it all works. The equations of PRT6 are very powerful in this particular regard. All this works, but your givens need to be sharp. Last 2 questions for this, and then we break on this part of the notes. The tip before, I've mentioned it a couple times, is the symmetry of free fall. Sometimes you will find with your givens, it is easier to calculate the displacement on the way down as opposed to on the way up. You can switch a VI to a VF, or a VF to a VI, and well, you'll see by practice. I don't want to talk too much on that now. All right, vertical launch. What is the velocity at the peak? Often called a VF. The velocity at the peak is going to be 0 meters per second. Vertical launch. What is the acceleration at the peak? Though this gets people thinking, oh, it's not moving, no acceleration. Acceleration is defined as a change in velocity over a time interval. This is an instant, not an interval. So if you look at any interval, no matter how small, leading up to or coming after the peak, neglecting friction, your acceleration is still 9.81 meters per second squared down. This has caught a lot of people on Regents exams because you forget about it by the time June comes around. All right, W35 is based on these 2 pages. W35 you all picked up. I also will have it for you shared. It's in the directory already. I shared with you over the weekend. 3.5 is front back of this singular sheet. Let's take a break there, and then I'll set you up in notes page 10.